Welcome to the PI University course, Introduction to LinkZero AX. Chapter 1, Introduction to LinkZero AX. LinkZero AX is the latest member of the LinkSwitch family of integrated offline switcher ICs from Power Integrations. Its unique feature is its ability to consume less than 4 milliwatts in off mode. When the feedback pin is pulled high for longer than 2.5 milliseconds, the LinkZero AX IC enters a power down mode, also known as remote off or most commonly off mode. In the circuit shown, this is done by connecting the feedback pin to the bypass pin. In off mode, the LinkZero AX device stops switching and the output voltage falls, but an internal voltage regulator supplied from the drain pin maintains a constant voltage on the bypass pin. Pulling the bypass pin to ground provides the reset signal to restart the supply. Putting the LinkZero AX device into off mode sends the supply into a deep sleep, reducing the total amount of input power consumed to 0.00 watts. Here's a chart showing input power in milliwatts versus input line voltage on the LinkZero AX Design DER260. At 230 volts input, the off-mode power is approximately 4 milliwatts. This is less than half that previously achieved with the industry-leading LinkSwitch CV. This 4 milliwatts is the power used by the entire power supply, not just the LinkZero AX control IC. International standards like IEC 62301 allow any power below 5 milliwatts to be rounded down to 0 watts. There are 3 parts in the LinkZero AX family, with maximum output powers from 3 watts with the LNK584 to 6.5 watts with the LNK586 in an open-frame, high-line design. To maintain acceptable operating temperatures in thermally challenged designs, such as ovens or external adapters, some power derating may be necessary. All devices are available in both SO8C and SMD8C service mount packages. Chapter 2, LinkZero AX and Appliance Applications. LinkZero AX ICs are ideal for any ultra-low standby application that provides a wake-up signal, such as a washing machine. In this case, the microcontroller would instruct the LinkZero AX IC to power down at the end of the wash cycle. The system would remain in off mode, consuming less than 0.00 watts until the user brings the supply back to life by pushing a button to start the next load of laundry. A LinkZero AX power supply consumes less than 4 milliwatts in off mode. To achieve 0.00 watts of system input power, we need to look at all areas of the appliance that could dissipate power. We have to minimize the leakage current through the Capacitor discharge resistors and any active circuitry connected to the DC input rail or the bypass pin of the LinkZero AX device. All of these circuit elements will consume power during off mode. As we'll discuss later in Chapter 8, Power Integrations CAP0 and SYN0 ICs can eliminate much of this wasted power. In ultra-low standby appliances, relays are typically used to completely disconnect the AC supply from the appliance circuits. LinkZero AX devices provide 0-watt input without the need for AC relays. This is important because, although AC relays do disconnect the entire circuit, they are expensive and sometimes still fail to eliminate all input power. Here's a simplified block diagram of the key systems in a washing machine using a traditional relay disconnect. The washing machine is turned on and off by a switch which can bypass the AC power relay and connect the internal circuitry to the AC source. When the wake-up switch is pressed, power passes through the EMI filter to the auxiliary supply, which starts up and powers the microcontroller. The controller then switches the main AC relay, latching the entire system on. There are some challenges to this traditional approach, including the cost of the high-voltage AC switch and relay circuit. There's also a significant amount of wiring needed to connect the AC input, typically located in the bottom rear of the unit, with the high-voltage circuitry which must be placed at the top front. This length of wire not only costs more, it causes problems for EMI filter placement. In this diagram, the EMI filter is shown in its ideal location for minimal standby losses, which is after the input relay. But for an EMI filter to be most effective, it must be as close to the AC input cable as possible. This means that the EMI filter must often be placed before the input relay, causing it to present a continuous load on the AC supply, increasing standby losses. This is why even relay-based designs often fail to achieve 0 power consumption in standby. Looking at this same block diagram using the LinkZero AX device, notice how much easier it is to implement the system. There's no AC relay or high-voltage switch. Instead of having an AC interrupt from the relay, a simple power down signal is delivered from the microcontroller to the LinkZero AX device. The LinkZero AX IC will bring the entire system down, reducing input power to extremely low levels. To wake up the LinkZero AX device, the user operates a low-voltage switch that briefly pulls down the bypass pin with either a soft switch or a logic input. The problem with this circuit is that the X-capacitor discharge resistors and line sense resistors remain connected to the AC source during standby and consume power at all times. To achieve the absolute lowest standby power consumption, these components must be isolated using PI's CAP0 and SYN0 energy-saving products. We'll look more at this in Chapter 8. Chapter 3. Introduction to power down and restart, and using the bypass pin as a driver. The LinkZero AX device will still provide power in off mode. Even while main switching is disabled, the bypass pin provides a regulated 4-volt output that can source up to 500 microamps. This provides a constant local auxiliary supply that can be used to power systems when the main appliance is in standby. For example, this supply can be used to power a motion sensor in a security system or an infrared remote control sensor for a TV. During normal operation, some of the bypass pin power is used to operate the LinkZero AX device itself, so the bypass pin can only provide 85 microamps. If you need more power, it can be supplied from the output rail or through a separate bias winding on the transformer. Here's a fully functional LinkZero AX circuit with a sensor connected to the bypass pin. To put the supply in off mode, the power down pulse turns on a transistor that connects the feedback pin to the bypass pin. This cuts off feedback to the device by pulling the feedback pin above its regulated 1.7 volts. After feedback is lost for more than 160 switching cycles, the LinkZero AX device enters off mode. The power down pulse must remain high for longer than 2.5 milliseconds to provide enough time for at least 160 switching cycles. This long duration also ensures that noise or transients don't falsely trigger off mode during normal operation. To wake the supply out of off mode, the bypass pin must be pulled below 1.5 volts. There's no minimum time for the signal, so only a few microseconds are needed. As soon as the bypass pin is pulled below 1.5 volts and released, the LinkZero AX device will immediately begin switching. We'll discuss this timing more in Chapter 5. During off mode, the bypass pin draws power from the drain pin to maintain regulation at 4 volts. Even though the bypass pin can source up to 500 microamps, you should aim to keep the power drawn from the bypass pin as low as possible, because any power draw will increase the standby consumption of the supply. During normal operation, the bypass pin can only source 85 microamps of current at 5.8 volts. If your system requires more power, you can use a small bleed resistor circuit like the one shown here to bias the rail. However, if your output voltage is too low to support 5.8 volts plus a diode drop, you'll need to add a transformer bias winding to power the bypass pin circuits during normal operation. Chapter 4. Isolated and non-isolated designs. LinkZero AX can be used in both isolated and non-isolated designs, as you can see here in the standard circuits for both configurations. In isolated designs, the opto-isolator provides both the feedback and power down signals. Chapter 5. Power down and wake up. In this LinkZero AX circuit, the supply enters off mode when a power down signal is used to turn on a simple BJT switch connecting the feedback pin to the bypass pin. During normal operation, the bypass pin operates at 5.8 volts. Connecting it with the feedback pin will raise the entire rail above 1.7 volts, cutting off feedback to the device. Once the LinkZero AX device has gone 160 cycles without feedback, it will enter off mode. The power down pulse must be longer than 2.5 milliseconds to allow sufficient margin for the full 160 skipped cycles. LinkZero AX ICs will always enter off mode if they don't receive feedback for more than 160 switching cycles. This means it's possible for a step down in load to induce an unwanted shutdown by causing a voltage swell in the output that may take longer than 2.5 milliseconds to reduce. To prevent this from happening, a small preload resistor can be added to the output to decrease output capacitor discharge time in case of a voltage spike. More information on this and other techniques to control shutdown are covered in Chapter 6. Once the supply is in off mode, waking it up is as simple as grounding and releasing the bypass pin using either a soft switch or a BJT. As soon as the voltage on the bypass pin passes below 1.5 volts and is released, the pin will recharge to its normal operating voltage of 5.8 volts. When it gets there, the LinkZero AX device will immediately begin switching to bring the output voltage back into regulation. Here are some waveforms from our DER260 design. The blue trace on the top is the 5-volt output. The yellow trace in the middle is bypass pin voltage, which is between 5.65 and 5.85 volts in normal operation. The purple feedback pin voltage trace stays at a constant 1.7 volts under normal conditions. The green power down signal is the voltage fed to the base of the transistor between the bypass and feedback pins. When activated, it pulls the feedback pin high for longer than 2.5 milliseconds, initiating off mode. We can see that when the feedback pin is pulled high, both the output voltage and bypass pin voltage start to fall. The output voltage collapses completely, while the bypass pin settles to its off-mode regulated 4 volts. There's actually a very small delay between the feedback pin being pulled above 1.7 volts and the output voltage fall, but it isn't visible here due to the long time base. Here are some more waveforms seen during shutdown. You can see the bypass pin voltage in pink, the feedback pin voltage below in yellow, and the LinkZero AX drain voltage along the bottom in blue, all with a much shorter time base. During the period immediately following shutdown, the bypass pin voltage hardly changes. When the feedback pin is pulled high, the LinkZero AX device immediately stops switching, but there's still some activity in the IC as it draws power from the drain pin while waiting to switch again. After 160 cycles of no switching, the LinkZero AX device goes into off mode and you see the drain go completely quiet. In this design, the LinkZero AX IC shuts down after 1.67 milliseconds, somewhat less than the recommended pulse length of 2.5 milliseconds. In off mode, the only voltage still regulated is the bypass pin. Now let's look at the wake-up sequence. Again, we see the 5-volt output in blue, the bypass pin voltage in yellow, the feedback pin voltage in pink, and a wake-up signal to the bypass pin pull-down transistor along the bottom in green. When the wake-up signal activates the transistor, the bypass pin voltage is pulled below 1.5 volts. When it's released, the bypass pin regulator brings the voltage back up to 5.8 volts. When it gets there, the LinkZero AX device immediately begins switching, bringing the output into regulation with a controlled soft start. Remember, there's no minimum time for the wake-up signal. As long as the bypass pin is pulled below 1.5 volts and released, switching will resume when the pin recharges to 5.8 volts. Chapter 6. Avoiding load step-induced power down. Now let's look at how load step affects operation of the LinkZero AX device in this 1.5 watt non-isolated design. If this design experiences a large step-up load, the output voltage will momentarily droop as current is provided from the output capacitor while the switching duty cycle increases to meet demand. The LinkZero AX device continues to receive feedback during this entire process, so there's no problem. If this design experiences a step-down load, the output voltage will rise, cutting off feedback until the excess energy on the output capacitor is discharged by the load. Remember from the previous chapters, if the LinkZero AX device doesn't get feedback for more than 160 switching cycles, approximately 2.5 milliseconds, it'll go into off mode, causing an unwanted shutdown. To prevent this from happening, we need to shorten the time to recover from a step-down load. First, add a small resistor across the output to quickly discharge the output capacitor after a voltage swell. This resistor should be sized to draw about 1% of full load current. Be sure to include the load drawn by feedback resistors R9 and R3 when calculating full load current. Second, we can increase the feedback circuit response to a rising output voltage by adding a capacitor in parallel with R9, the upper feedback resistor. This allows the signal to temporarily bypass R9 during a fast output voltage transition, reducing the feedback loop response time and limiting output voltage rise. Chapter 7. Capacitor forming and its role in low no-load power consumption. The input power of a LinkZero AX design in off mode is so low that even a few milliwatts of error can make a measurable difference. This makes accurately calibrated equipment and proper testing procedures extremely important. For help with setting up your equipment to accurately measure very low input power, please see the PI University course, Testing Compliance to Energy Efficiency Standards. Here's a chart measuring the input power of a brand new LinkZero AX DER260 board versus time at 230 volts AC input. To confirm accuracy, this input power was measured by two different wattmeters, and both traces are shown here. Notice that when the voltage is first applied to the board, the input power is much higher than expected, but drops off rapidly and settles in the expected range after about 30 minutes. This phenomenon is a result of the manufacturing process of the electrolytic input bulk capacitor and is only seen during the capacitor burn-in period. The insulation layer within an electrolytic capacitor is formed by an electrochemical process which occurs when a voltage is applied across the capacitor for the first time. It can take up to 30 minutes for this insulation layer to fully form and for the leakage to reduce to its final steady-state value. Again, this process only occurs during the first few minutes of an electrolytic capacitor's life and is typically described in the manufacturer's datasheet by a plot similar to the one shown here. Notice that the burn-in leakage curve from the datasheet very closely matches the standby input power we measure on the left. For the most accurate input power measurements, we recommend waiting at least 30 minutes after first powering up your new LinkZero AX design before taking data. Chapter 8. Applying LinkZero AX, SynZero, and CapZero devices to an appliance. LinkZero AX ICs provide a very simple circuit for controlled power down and wake up. But because this method doesn't use any relay circuits, the AC supply is always connected to the entire system, including the auxiliary power supply and EMI filter. A typical appliance circuit may use X-capacitor discharge resistors in the EMI filter and line sense resistors for the microcontroller. These resistors are a constant load on the input, even during off mode, increasing standby consumption. For the lowest possible standby power, CapZero and SynZero devices should be used to disconnect the discharge resistors and sense resistors when they're not in use. CapZero and SynZero ICs both consume less than 1 milliwatt of input power. Together with the less than 4 milliwatts required by the LinkZero AX device, they provide a complete low-power circuit without the complexity found in traditional relay designs. More information on SynZero and CapZero devices can be found on their corresponding pages on the Power Integrations website. Thank you for attending the PI University course, Introduction to LinkZero AX. If you have any comments or questions, please email piuniversity@powerint.com.